Okay, our next presentation is by Dr. Yize Zhang. And this presentation, he's from the Shanghai Astronomical Observatory. And his presentation will be on real-time multi-GNSS orbit and clock combinations at SHAL.
Okay, thank you for introduction. My topic is real-time multi-GNSS orbit and clock combination at SHAL. So first is the background. IGS started to provide real-time service for more than 10 years, and we also have the real-time working group among IGS. This table summarizes the IGS real-time service. Thanks for Dr. Ningbo Wang. And there are more than 10 analysis centers provide real-time products. All the ACs provide real-time orbit and clocks, and some of them also provide code and phase bias or even VTEC. All the ACs support GPS system, and some of them also support GLONASS and Galileo system. And currently, 7 ACs support BDS system. These products, the performance of different ACs are vary. So it is necessary to provide combined real-time products. Currently, we have IGS 02 and 03 combined products. However, there exist two main issues of the real-time products. The first one is the product interruption. As shown in the right figure from ESA, we can clearly see the data product interruption. And another issue is the product jumps. This is often observed in the combined product. This is probably due to the error or bugs in the combined processing. As a result, the current RTS products, the reliability and robustness of the real-time products compromise. So the existing studies mainly focus on post-processing combination or real-time GPS-only combination. For other systems, such as BDS, the product interruption and jumps still exist. Here, we use 1 month of data from the IGS combined products to evaluate its performance. The data is from this January in this year. For GPS and Galileo, orbit accuracy, the RMS is well within 10 centimeter, and for the standard deviation of clock or radian minus clock is also well below several centimeters. This is at a similar level with current individual analysis centers. However, when it comes to BDS, the accuracy becomes worse, especially for the clock. If we take a detailed observation of the time series of the clock, we can clearly see frequent clock jumps for BDS satellites. These jumps can be as large as several meters. So this is a big issue. Here we also take example for January 16 this year between 2 agent epochs. For the first epoch, the orbit accuracy of the IGS combined products is several centimeter. However, when come to the next epoch, this difference becomes more than 20 centimeter. On the same day of the clock products, here we present 2 BDS satellites, PRN 21 and 22. We can clearly see that PRN 22 shows frequent clock jumps. So as a result, we can clearly see for orbit and clock, there are frequent jumps for several satellites. So it is necessary to develop real-time orbit and clock combination software. The conventional combination method is designed for post-processing. The key processing is the iterative waiting strategy. However, for real-time combination, we need to carefully handle the pre-processing due to data interruption. For real-time orbit combination, currently IGS use fix a specific analysis center and only combine the clock products. However, we think it's better to also combine real-time orbit because we think that combined orbit also performs better than a single specific analysis center. Here we use a sliding window weighting strategy to decide the weight of each satellite for each analysis center. For real application, we choose the sliding window for 30 minutes. For real-time clock, before combination, we need to correct the radial residue after orbit combination, and we also need to correct clock datum by linear trend removal and initial clock alignment. The figure on the right shows the clock time series after the data correction. For real-time clock, there is an issue of data interruption. This interruption is either on one AC or one specific satellite on the right. So to address this issue, we propose an inter-epoch difference strategy to determine the clock data. In this strategy, we use epoch difference clock of all the valid analysis center to decide the data change between two epochs. After applying this strategy, for example, for these four ACs from around 450, the AC number decreased from 4 to 3. And after applying this strategy, the combined clock becomes continuous and there's no jumps. So to summarize, this is the flowchart of our real-time orbit clock combination. Different from the post-processing method, we add the sliding window for orbit orbit combination, and we do the clock basis pre-processing during clock combination. So here are some results of our method. Here we use 1 week of BDS real-time products from 4 ACs. We can see that there do exist data loss for each AC at maybe with different level. The orbit combination weight for each AC are consistent with their own orbit accuracy, as we can see the table and the figure on the right. For the product completeness, the combined products are higher than any individual and IGS combined products. And for the orbit accuracy, the combined product is much higher than IGS combined products. And at the similar level with the best AC. Here, the best AC is Wuhan University. This is expectable since our goal is not to achieve the best accuracy, but to have better stability and completeness. And when it comes to the clock accuracy, the standard deviation is within 0.3 nanosecond, which is better than most AC and the IGS combined product. This conclusion also applies to the standard deviation of CISA. For PPP validation, we test on 27 IGS stations. The positioning accuracy is also better than the IGS combined product and is comparable to Wuhan products. So to summarize, we use a sliding window weighting strategy and inter-epoch strategy to resolve the issues during real-time orbit and clock combination. And the PPP performance is improved. And our real-time combined product is under test at our own server, is named SSI00COM0. So we are prepared to contribute to IGS RTS combination. Thank you. This is Zhang.